Hey there, physics enthusiasts. Get ready to dive into the world of forces and motion in Super Titans Tutoring latest series. Today we'll be uncovering Newton's laws, going over how do they govern our systems, how do they govern the universe, what is Newton's secret, and how do we apply this to exam questions. Part one will go over Newton's first law and Newton's second law, which will be followed by part two in our series, which will go over Newton's third and Newton's gravitational law. For today's purposes, we'll be going over the 2023 IEB paper one, question 5. Do have it in your books, do have it close to you. We will not be going through every single question, but specific questions. Let's start with Newton's first law, also known as the law of inertia. But first, what is inertia? Inertia is an object's resistance to change in its motion. Objects with more mass have more inertia, meaning they're harder to stop moving. So imagine a ball, just a perfectly happy sitting ball, just still no one has touched it. And this ball will stay that way unless something happens to it. That on its own is inertia in action. But when someone comes and moves the ball, kicks it, throws it, whatever, picks it up, that over there is when we have a change in the ball's motion, which then goes to Newton's first law, which states that an object at rest and an object in motion stays in motion with the same speed in the same direction unless acted upon by an unbalanced force. What does it mean when we say it's in the same speed, the same direction? Essentially, it just means objects are stubborn. They enjoy doing what they've already been doing and they will continue to do what they were already doing. If they were resting, they'll continue to rest. If they're moving, they want to keep moving at the same speed and in the same direction, unless a push or a pull, i.e., a force, is applied onto them. Again, think about everyday activities. If you're having coffee, the mug is on the table. Unless you pick it up, it will stay on the table. Think about a ball. As long as it's on the ground, it will stay there unless it's kicked, it's picked up, or some action is performed. This then brings us to Newton's second law. So we've acknowledged that a ball will only move once some action, some force is applied onto it, which leads us to Newton's second law, which is essentially stating that the more force you apply to an object, the more it will speed up or change in direction. And the mathematical formula is as followed. F is equals to ma, which essentially just means the force is equals to the mass times the acceleration. Remember, if you're not given acceleration, but you're given velocity, or maybe you're given distance, or you're given time, or you're given some other value, remember you can always get acceleration using your laws of motion, your equations of motion, actually, right? And this should be something you always remember. In order to best understand force is equals to mass times acceleration, we're going to look at three scenarios to see how does the relationship work between force, mass, and acceleration. In our first scenario, what we have is a single person who is pulling some object with a force F as well as a mass m and is accelerating at a. This is a basic illustration of Newton's second law, where the force applied is directly proportional to the acceleration. So the force applied is directly proportional to the acceleration, and the mass as we assume the mass as constant, right? And because of this, what we understand is that a greater force will then result in a greater acceleration because these are directly proportional. So if F increases, A increases. If F decreases, A decreases. Great. Scenario 2 then looks at two persons that are pulling the same box M, no increase, with an acceleration of 2a and a now force of 2a. What is happening here is with double the force, because there are now two people applying this force, we have a doubled force, which will result, as we say, because the mass is constant. If we have 2F, we should have 2A. As long as force increases, what we're saying is that acceleration will increase by the same ratio as a result of them being, again, directly proportional when mass is constant. Very important, mass is constant. But what other scenario? Now we've looked at force, we've looked at acceleration. We've looked at how does force affect acceleration and how does acceleration affect force at constant mass. But then what happens when our mass changes? And that is scenario 3. In scenario 3, we see the same one person who's applying a force F. Acceleration is now A over 2, and mass is now 2m. So our mass has been doubled. With our mass being doubled, what we see is that our acceleration is halved. So we have 2m, which is resulting in a over 2. Why is our acceleration being halved when m is being doubled? And that is because we are demonstrating an inversely proportional relationship between our mass and our acceleration. So mass is inversely proportional to acceleration. And so as long as mass is increasing, when force is constant, again, as we have seen, F is constant, as long as mass is increasing, when force is constant, what will continue to happen is that acceleration will continue to decrease. Practically speaking, if you try to push a car versus pushing a truck, it will most definitely be harder to push a truck at the same acceleration as it would be to push the car because a car has less mass. But if you try a bike, a car, and a truck, you'll have the bike first, you'll accelerate fast as you push it, followed by the car, and followed by the truck. And all of this just demonstrates Newton's second law, which is force is equals to mass times acceleration. Okay, great. And you might find yourself wondering, what happens when acceleration is constant but mass and force? As the force increases, right, provided acceleration is constant, so let's assume acceleration of 9.8, right, a rocket launch, for example. As the mass increases, the force is going to increase as well. And the reason for this is because it needs to be able to maintain constant acceleration. And the only way that it can maintain constant acceleration is when force increases at the same rate that the mass is increasing. So if the mass increases from 2m, the force also needs to increase by 2m to keep A constant. And that is always how it will work because we're always trying to maintain one or the other. There's something that we need to maintain at every given point. Here we see that we are maintaining the mass being constant. So if acceleration increases, force needs to increase. Here we're maintaining the constant force, which is achieved by looking at the inverse relationship between the mass and the acceleration. Now, let's look at the real world problems and how this has actually been applied to physics papers. Again, reminder, we're using IEP 2023 question 5. So the question reads, two blocks A with the mass of 1 kg and block B with the mass of 5 kg are pulled along. Okay, so we know there's some pulling that's occurring along a horizontal surface. We've got a surface by rope 1. So rope 1 is responsible for the pulling. They are connected by rope 2, and these have rope 2 as the connection. So we're just going to write it down here. This is where they're connected, and rope 1 is where the pulling occurs, right? While they're moving, block A experiences a frictional force of 3.9. And before we even go forward, do we understand what frictional force is? Make sure you ask yourself, do I understand what frictional force is? And frictional force is an opposing force, simply put, right? It's the force that opposes motion between two surfaces that are in contact with one another. So this is an opposing force. And remember, the two surfaces have to be in contact with one another. So block A is experiencing the force of 3.9 newtons, whereas block B experiences a frictional force of 19.6 newtons. And so just from that again, what we're seeing is that block A has a much lower force, frictional force, than block B, which would mean that somehow, based on what we see here, our masses, block A receives more resistance from block B. Okay? So let's just look at what forces are acting on each of them. What forces are acting on rope B? The two forces acting on rope B are, like we said, we have a frictional force, which is not opposing, and because we have rope 2 that's connecting these two, that's allowing for the pulling when this is being pulled forward, we have an applied force here, which we can the tension force. Right. And the tension force is a reaction force. What that means is that it arises in response to other forces acting on objects. Right. So the reason we have the tension force is because we have an applied force and it's arising as a reaction to this. Right. We also have a frictional force which will be in the opposing direction, and we have our normal and our gravitational. But as we're working on a horizontal surface, we don't really care about Fn and F, but they do exist. Now, what is happening on block A? Got block B. So block A, first and foremost, experiences tension from rope 1. We have Ft occurring here. What else is happening? It also experiences some force right, over here, as it's the tension over here from rope 2, from block A to block B. From block B to block. From rope 1, the tension that's experienced is the tension that's pulling it backward. From rope 2, the tension that's experienced is this one that's pulling it backwards. And the reason it's being pulled backwards is because it's a reaction to block B pulling it. Like we say, block B has a much greater resistance on block A. Correct. And we also have our frictional force where it's moving it that's acting back. Okay. Now remember how Newton's second law works. The net force on each of the blocks will determine its acceleration. We can see that the net force on both the blocks is in the forward direction, right? We see Ft rope 1, but the size of the net force will be different for each block due to the two different masses. We've got 5 kgs here and we've got 1 kg. Now, a few scenarios that we can consider. Scenario 1 is if rope 1 pulls harder, the tension in both the ropes will increase, which will lead to an increased acceleration, right? Only if the friction doesn't change. So if rope 1's force increases, we have an increased force in rope 2, which will result in an overall increase in acceleration, considering the fact that that friction does not change. Scenario 2 could be if the surface gets rougher, what will then happen? So if the surface gets rougher, friction increases. If friction increases, what happens to acceleration? Acceleration will decrease, right? Because acceleration is in the direction of motion and friction is in the opposite direction. Friction should be opposing that and should be slowing down the acceleration altogether. Then, if rope 2 snaps, so let's assume rope 2 snaps. What is then going to happen? The whole system could change, right? And by breaking the forces on each object, right, we can kind of predict how they'll move and solve problems based on how they'll move if now we're just looking at rope 1 alone, which is now only being pulled by, we're looking at block A alone, which is now being pulled by rope 1, and we have block B, which is not being pulled at all. So what then happens? Okay. Now moving to the velocity time graph. So we're told that after rope 1 has pulled the system for 0.5 seconds, rope 2 snaps, right? What we understand is that rope 2 is connecting block A and block B. We also understand that there's some force. Block A is experiencing much greater friction because block B is pulling it back, right? So now if this snaps, what we expect is that block A experiences less stress than when it started, right? And so then we're told that the velocity of block A is represented against the time on the graph below, which is not drawn to scale. So now we see our velocity time graph, right? Let's analyze the motion. So from 0 to 0.5 seconds, we see that the line is slanted upwards, which just means over here, block A is accelerating and it's gaining speed over time, right? And another way we know this is because our change in our velocity over our change in our time is equals to our acceleration. And then we understand that our acceleration can be decelerating or accelerating. But the steeper the graph is, steeper graph means you've got a higher speed, right? Or instead, let's say higher acceleration. And so we see that from 0 to 0.5, where the two of them are connected, it's slanting upwards, but not at we see like it's increasing, but not so much that the acceleration is drastic. But then at this point right here, what happens? The rope snaps, rope 2 snaps, right? And when rope 2 snaps, what we understand is that rope 2 snapping means that there's now less stress on block A. So block A was moving slower, if we think about it. It was accelerating slower because it had to carry on this load. But now block B is gone, right? So that's going to cause a sudden increase in velocity in a short time. So this is the increase that we see in a very short time. Because now rope 1 is only pulling block A, and block A also doesn't have the stress. Block A doesn't have the stress of block B anymore, right? So what we can assume when we're doing this is, first and foremost, block B, just by looking at this, when block A snaps, when rope 2 snaps and then the two go aside, block B will probably go slowly until it comes to a stop where it reaches a velocity of 0, right? Block B. We don't know at what time it's going to happen, so just an estimate. But we also know that block A is having an increase in velocity from 0.5 to 0.553 seconds. But after 0.553 seconds, even though we don't have the data, we can infer that block A will start to slow down due to friction. So after this point, block A will probably slow down due to friction. So it's a rapid increase over a short time. Friction. So that's essentially what's happening. We understand that another thing that causes this quick increase is that, like we said, rope 1 initially, let's add rope 1 to our top. Rope 1 was taking on the weight of block A and block B, right? So that means the tension in rope 1 had to be acting on both A and B. But now that it snaps, the tension on rope 1 is only acting FT. Instead of acting on both, it's only acting on block A. Right? And that's another reason that we see that it's now starting to accelerate a lot faster. Hence this. So rope 1, as well as the fact that block 1 is experiencing a less pushback from block B. Now, how do we bring this back to Newton's first law? So again, Newton's first law says F is equal to ma. Right? Before rope 2 snaps, the net force on block A was smaller due to the opposing tension from rope 2. Right? So before the snap, we expect a lower F net on block A because of the opposing tension. But after the snap, as we can see, acceleration is also increasing. And remember what we said, F is directly proportional to A. So once A increases, F is also going to increase. That means after the snap, the net force that's acting on block B is also going to increase significantly, which causes the rapid acceleration that we see in the graph. Right. And remember that we're able to calculate acceleration using the values that we already have and understand what's going on at those values just by using the graph. Okay, so now let's go into the questions and see what is next. From now that we understand what has happened in the graph, we understand the rapid increase from 0.5 to 0.553 seconds. We also understand that at the same time where the snap occurs, block B will start to lose speed, right? Until it gets to a stop because it's no longer being pulled and there's nothing that's causing it to move. And additionally, block A, in a short space of time, it'll gain a lot of velocity and it'll accelerate a lot faster. Hence, we also see that this line over here is a bit steeper than this one over here. So we know that means that is a faster acceleration. Yeah. Let's look at the questions. We've looked at the pictures themselves. Let's look at what do the questions actually want and how much of them have we answered. So use the velocity time graph to calculate the magnitude of the acceleration of the system while the force of rope 1 is being applied before rope 2 snaps. So we're looking at the first part of the graph. Draw a labeled free body diagram showing the horizontal forces acting on block B in the first 0.5 seconds. Describe the relative size of the forces must be clear. Again, it means they don't have to be 100% accurate, but we should be able to see what actually happened. Calculate the tension in rope 2 before it snapped and determine the magnitude of the force that rope 1 was exerting during the first 0.5 seconds of motion. Okay, so now let's go over the first question and understand what does it actually mean and what does it entail. So we're supposed to use the velocity time graph to see what happens within the first 5 seconds, right? So before the snap. So we start at 0, 0 initially. We could say this was our initial. And we end off at 1.2 meters per second and 0.5 seconds. So we know acceleration is equal to the gradient, which is the change in the velocity over the change in time. And so that means it's 1.2 meters per second minus 1 over 0.5 seconds. Right. And so if we just divide the two, we're going to get 2.4 meters per second. Right. 2.4 meters per second minus 2, which we know acceleration is always the power of minus 2 because of the 2 seconds that we have over there. Right here. And remember, not a math lesson, but this just comes from maths. If you've got s minus 1 over s, and we know that if you've got two exponents are going to subtract each other, so if you have s together, it's going to be s minus 1, which will give you s minus 2. So just a quick recap from that. So now we've got 2.4 meters per second. What does this mean? It just simply means that our system is speeding up at a rate of 2.4 meters per second every second. Remember, units are important. Did I explain it over here? Units are important at every point. You can lose marks for not, you will lose marks for not having your units. Units, very, very important. Very important, very important. And know which units to go for. Again, we're going to see that if you try it yourself, try to calculate acceleration at this point, you're going to see that this acceleration is actually higher than the first acceleration that we see. And the reason for that is because of Newton's second law. Right. And that acceleration is due to the net force that's acting on the system. So we'll always come back to Newton's second. Okay, the next question was to draw a free body diagram. So as you remember, in the first part of this, we already acknowledged what forces act on B. Now, remember that the forces acting on block B were our tension, Ft from rope 2, and our frictional, right, in the horizontal. So as we draw it, the black dot will represent block B in a free body diagram. We know we have an opposite force acting at 19 newtons, which is our frictional force, our opposing force. So we're going to draw it this way and draw the arrow towards the side where it's going. So if. Now, in order for this block to actually even get pulled forward, your frictional force cannot be greater than the force that's being applied on the opposite side, or which then results in a tension force that we see. So our tension force needs to be higher, right? So we could say it needs to be longer. It needs to show a longer arrow, which indicates that the tension force is greater than the frictional force, which will make the whole system possible. So let's draw a longer line. And this will be Ft, which is our tension force. And now, based on our relative sizes, we can see that our tension force is greater than our frictional force, which is what we would have had to mention. Okay. And remember, the reason, again, I'll just stress this again, the reason this side will be greater than this side is because we need our net force is in the forward direction. And because our net force is in the forward direction, block B would accelerate in the forward direction. If our net force was in the opposite direction, it would mean that our frictional force is actually greater than our tension force. If we have a system like this and somehow our net force is on the opposing side. Okay? So we want to calculate the tension in rope 2 before it snaps. We understand that rope 2, its tension is affected by both block A and B, that means. So we're just going to put our free body diagram because it's still visible. And we know that it's got a frictional force acting the side, and it's got our applied force acting the side. Our applied force, i.e. our, what is a tension force? Ft. And we need to recall that Newton's second law states that F is equal to ma, where F is the net force. And in our case, the net force acting on block B, we're going to concentrate on block B. The net force that's acting on block B is the difference between The net force that's acting on block B is the difference between the tension in rope 2 and the frictional force. We can see the opposites. We're saying this is positive. We're going to choose forward as the positive direction. So that would mean the frictional force is the negative. So if we decide to say, we're going to say Ft, which is our tension force, plus minus Ff, because we're saying that we're choosing our positive direction as this direction, right? And so that will be Ft minus frictional force is equal to Ma. We already know what our mass is, which is 5 kgs. But not just our mass, we're also aware of what our acceleration is, because we calculated it previously as 2.4 meters per second. We also know what our frictional force is, as this was given in our question as 19.6 newtons. So we're going to put that in this formula to work out the tension of rope 2 before it snapped. So we're going to say Ft minus 19.6 newtons is equal to Ma, M being 5 kgs, and A being 2.5 meters per second. So if we do the math, we're going to end up with our tension being 31.6 newtons. So T2, which is the tension of rope 2, is going to be equal to 31.6 newtons. Okay, so what we need to remember before we move on to the next question is that this same tension force that we're seeing here for the tension of rope 2, this same one is the one that we're going to see acting on block A in the opposite direction, but the same one that we're going to see acting on block A, which we'll see in the next. Determining the magnitude of the force that rope 1 was exerting during the first 0.5 seconds of motion. During the first 0.5 seconds of motion, remember, block A and block B have the same acceleration, which is 2.4 meters per second squared. Okay? The tension that's being faced by block A is in the opposite direction. So if this is block A, we'll be focusing on block A. We know that we have a tension force, we know that we have a frictional force, and then we know that we have another tension force from rope 1. This is rope 1, rope 2, and the tension that we see, right? So we're going to again take this way as positive. What that means is following our Newton's law, which is F is equals to ma, and acknowledging that block A's mass was 1 kg. So we've got F is equals to ma. That means Ft to get net, plus we're just going to add them all up. We're going to say Ft plus minus Ft for rope 2. So we're going to say Ft2 plus minus frictional force is equals to ma, which simply becomes Ft minus Ft2 minus frictional force will give us ma. So we've calculated Ft2, the tension of rope 2, and we know what our frictional force is as it was given to us. All we need is T1, right? And so, and we know that M is 1, A is 2.4. So we're just going to do the math, substitute first. T1 is equals minus, let's just keep it as is. So we're just going to say minus, tension squared, we just calculated as 31.6 newtons, 6 newtons, minus our frictional force, which we have as 3.9 newtons, which is equal to 1, which is our mass, and 2.4 meters per second, 1 kg. And so this will give you a tension of 37.9 newtons. T is 37.9 newtons, which is what we expect because we need rope 1 to have a higher tension so that it's actually able to pull and ensure that the net force that's experienced is in the forward direction. But remember, after the snap, the force exerted by rope 1 would only need to overcome the friction on block A, which will result in, again, a much greater acceleration on block A. Hey, that wraps up part 1 of our exploration into Newton's laws of motion. We've covered a lot of ground. We learned about inertia and how it governs objects at rest or in motion. We explored how force, mass, and acceleration are connected through Newton's second law. We saw how these laws apply in real world problems using free body diagrams as well as calculations. But the fun does not stop here. In part 2 of this series, we'll dive deeper into the world of forces, looking at Newton's third law, discovering how every action has an equal and opposite reaction, additionally going into gravitational force and covering the force that keeps us grounded and the planets in orbit, and even more. We'll tackle more challenging problems, see how these fundamental laws shape our understanding of the universe. And matrix, look out, we will have one that does show the relationship that we see with Newton's second law and momentum. Additionally, just to give yourself a bit of a challenge, try to look at the velocity time graph that we had and see at the same time between 0.5 seconds and 0.553 seconds, what would happen to block B? Question 5.7. So keep watching, hit the subscribe button, get notified when part 2 drops. Follow us on our socials, which will be in our link for more physics fun, accounting fun, chemistry, everything, math, English, and beyond. Thanks for joining me on this physics adventure. Keep exploring, keep questioning, and keep your passion for science alive. You can do it.